So in previous video, even though I told you as if I gonna discuss about 6 component stress state and their transformation, actually it's really tough to derive the entire tensor transformation without the proper education of linear algebra. So without using the concepts of linear algebra, yeah, and the concepts of tensor, yeah, what can you do as an undergraduate is limited problem. So what you're gonna consider is plane stress problem. And what is plane stress problem? So when you have a element, subjected to some stress state, we call, it is a plane stress if sigma z is 0 and tau xz is 0, tau yz is 0. Okay, so in this problem, yeah, we don't have any stress component involving the component out of this plane. Of course, instead of z, it can be x, it can be y. Okay, but at least 3 stress component related to one axis must be all 0, so that we only have 3 independent variables and the other 3 is completely 0. Okay, so for this plane stress problem, we can derive the transformation equation relatively easily, and we can also convert that transformation equation into the graphical representation called Moore's circle. Okay, so the focus of the today's lecture and our ME tutorial will be transformation of plane stress only, and regarding the general stress state involving 6 variables, yeah, we're gonna give you, I would say, more like a empirical and heuristic approach in some lectures to come. Okay, so let's consider this problem. Only sigma x, sigma y, and tau xy are given as variables, and the other component is given as 0. Okay, so the question we're gonna ask is, what will be the stress with respect to new axis x prime y prime. Okay, so for xy prime, y axis, we define sigma x, sigma y, and tau xy. Instead of this, somebody may ask, if we set up x prime axis, y prime axis, and suppose that the rotating angle is theta. Okay, then for exactly same stress state, what will be the numbers if we consider x prime and y prime axis? Okay, so that's the question. So to answer this question, of course, along the x prime y prime axis, what you can imagine is it will be sigma x prime, it will be sigma y prime, and tau x prime y prime. Okay, so we want to obtain the relationship between sigma x, sigma y, and tau xy with respect to xy, and exactly for the same stress state but different coordinate system, what will be different readings. Okay, so that will be the topic of this lecture. Okay, so to do so, what we're gonna do is we're gonna take our area of interest as this red block, which is given as this. Theta is the angle rotated from the original coordinate system xy. Okay, then if we consider this triangular volume, then we have the following stress component. We have sigma y at the bottom, sigma x at the left hand side. We have tau xy at the left hand side and bottom. And for this inclined surface, we have sigma x prime, tau x prime, y prime. Okay, so with this, at least for single body, we can have some stress component in xy and some stress component in x prime, y prime coordinate system. Okay, so given this, and let's also define the area of inclined surface as delta A. Let's try to draw free body diagram. Because stress is a force per unit area, to obtain force we have to multiply the area. So for this inclined area where we define area as delta A, we multiply delta A to obtain the force acting on normal direction and the shearing direction for left hand side and right hand side, because we have similar area, delta A sine theta and delta A cosine theta. Yeah, we multiply this area to the stress component to obtain the force acting on this infinitesimal volume. Now, after defining these forces and free body diagram, we can try to write down the force equilibrium equation. So we're gonna draw force equilibrium equation along x prime axis and along y prime axis, and force sum must be 0 for each directions, right? So along the x prime axis we have this guy, and along the x prime axis, that this term does not contribute at all, because there is 90-degree angle, so no projection on x prime. And from this sigma x delta cosine theta, we have to take only x prime projection, which is this guy multiplied by cosine theta. And from this tau, we have to also take the projection to x prime direction, right? So after this, we have to multiply sine theta to reflect the x prime projection, and we have to do same thing for sigma y delta a sine theta and tau xy delta a sine theta. Okay, so then there is 5 terms, 1 2 3 4 5 term that is along x prime direction, and only this guy has positive sign and the other terms have negative sign. And we can do exactly same thing for the y prime axis along this direction. So along that direction, the contribution of x prime sigma x prime delta a is 0. We only have full contribution of this guy. Then we have the other 4 force component, and there is positive and negative contributions here. So after deriving force summation along x prime, force summation along y prime, then what we can do is we can massage this equation and try to simplify this. Okay, so if we move this guy to the left hand side and divide the delta a to both sides, and delta x prime can be written as these, and tau x prime y prime, starting from this equation, if we move to this term to left hand side and summing up the right hand side 4 terms and simplify it, we have these terms. Okay, so what we have found is we can represent sigma x prime in terms of sigma x, sigma y, tau xy. We can represent tau x prime y prime in terms of sigma x, sigma y, and tau xy. Okay, and instead of taking this red volume, if you take the red volume like in this way, then what we can do is we can also derive sigma y prime in terms of sigma x, sigma y, and tau xy. I will leave this to you. Not gonna make a full detailed discussion about this. You can plot your own free body diagram and try to derive an equation for sigma x prime. Now, having obtained this equation, what you can also see is we can use a trigonometric equation to replace cosine square and sine square term using cosine 2 theta and sine 2 theta term. Okay, it must be 2 sine 2 theta. Okay, then after replacing cos square, sine square, and sine theta and cosine theta term, and after plug this into the position of cosine square theta, sine theta square, and sine theta cosine theta, then you're gonna end up having these 3 equations: sigma x prime, sigma y prime, tau x prime, y prime, and in terms of sigma x, sigma y, and tau xy, and cosine 2 theta and sine 2 theta. Okay, so after massaging up these equations, we can find some graphical meaning and the analogy between these set of equations and another set of equations that we have learned back in freshman calculus class. So if you have really nice and amazing memory, yeah, because there is analytical equation relating sigma x, sigma y, and tau xy with sigma x prime, sigma y prime, and tau x prime, y prime, you can simply use this equation. But for most of us who does not have such a good memory, instead of memorizing the entire equation, we want to have a better way to memorize this. Okay, so to find a graphical representation, let's try to do some massage about this equation as I told you. So first observation we can make is, let's try to sum up equation set 1 and equation set 2. Okay, if you sum up equation 1 and equation 2, which result in sigma x prime, sigma y prime, then what you're going to find is like all the other terms will cancel out, such as the sine 2 theta term. You're gonna ends up having the right hand side summation will be sigma x plus sigma y. Okay, so what it means is that for this stress state, if you have xy coordinate system and if you have x prime y prime coordinate system, under this coordinate notation, the reading for sigma x prime plus sigma y prime is conserved. Okay, so the even though you rotate the coordinate system, at least the sum of normal component will be conserved. Okay, so this is the first observation. And second observation we can make is it's a little bit complex. If you subtract second equation from first equation and divide that by 2 and take the square, and if you also take the square of third equation, and if you consider this in left hand side, and after massaging this equation, I'm gonna leave this to you because it's tedious job, and you can confirm this by yourself, and I don't want you to follow this tedious job in this video lecture. And what you're gonna find is it'll have same value for original xy coordinate system. Okay, so under the coordinate notation we found two conserving quantities, sigma x plus sigma y and sigma x minus sigma y divided by 2 squared plus tau xy squared. Okay, so these two quantities are conserved quantities. Okay, so if you define a average normal stress as sigma average as sigma x plus sigma y divided by 2, it will be also constant or conserved on the coordinate notation. And what you can also write this equation sigma x minus sigma y over 2 is that instead of this you can write down sigma x minus sigma average. You see that this equation and that equation is equal to each other because after subtracting this it becomes sigma x over 2. You have minus sigma y over 2 here, so left and right equation are equal to each other, and you can rewrite this as sigma average. So this term can be written as sigma x minus sigma average squared. Okay, and regarding the second conserved quantity, you can rewrite the equation as sigma x minus sigma average squared plus tau xy squared is conserved. And let's define this quantity as r squared, some constant. Okay, so this constant will be conserved under the coordinate notation. For xy coordinate and rotated coordinate with theta angle, arbitrary angle theta, sigma x prime y prime, this is also conserved. Okay, so what we can found is that after finding this conserved quantity, we can rewrite equation 1 to 3 in previous page using sigma average and average. Then you can write down and in simplified way in this way sigma x prime, sigma y prime, and tau x prime y prime. Okay, so these equations, after moving this to here, moving this to left hand side, okay, you're gonna have this entire term, something cosine 2 theta, something sine theta. You have this entire term, something similar, cosine 2 theta minus tau xy sine 2 theta, and you have tau x prime y prime equals to be another something similar term, and you have tau xy cosine theta. You have a sine 2 theta here with the negative sign. You have a cosine 2 theta and you have a cosine 2 theta here. So this reminds us of something we have learned in calculus, and in the next video we'll try to make an analogy between this equation and the vector transformation or vector rotation equation we learned back in calculus. Okay, so please remember that this is pure equation massage, and if you have super good memory, forget about this. You can just rely on this. However, because most of us do not have such a good memory, we are trying to do a lot of equation massage and try to find some sort of way to memorize the equation 1 2 3 more efficiently. Okay, of course, even though you have super good memory, because the we're gonna teach you how to memorize this equation graphically, you have to learn what Mohr circle is. Okay.